of our seminar. Thank you very much, good lady. So our speaker is doctor after 5 minutes, we hope, Hun Chu, and he will remind us. He is a student of well known to us Timur Reutberg, who is present, and now he will remind us his title, and he will begin. So please begin.
Thank you very much for introducing me, and thank you for having me to speak today. Yes, so let me share my screen, and I can start talking about my topics.
Yeah.
Do you see my screen?
Yes.
Okay. So please, if I'm not clear at any point, please interrupt me and ask me questions.
Yes, they like to interrupt our listeners. Don't worry.
Okay. So today I will talk about the thresholding gradient algorithm, or the TGA, and how we might relax the optimality for the algorithm. This is the outline. In section 1, we will discuss the TGA and some properties that will give us some information about how the TGA behaves.
Remind us, please, what is TGA once more?
TGA is the thresholding greedy algorithm.
Good.
Yeah. And in section 2, we will talk about almost greedy or greedy basis. Section 3 and 4 will be about greedy type basis. So this is a new notion that we introduced in our project. Section 5 will look at the equivalence between what I call greedy and almost greedy basis. So these are the this is the outline of the talk.
Yeah.
So the thresholding greedy algorithm, or the TGA. So here is a setup. Let X be any separable Banach space, infinite dimensional, over the field F is the real or the complex numbers. Let X star be the dual of X. Then a basis of X is any collection, countable collection En in X, such that the closure of the span of En is equal to X. And there exists a collection En star in the dual, such that En star En is the canonical delta function Nm. This is also called the bi-orthogonal functional of the Ens. The last property is that the norm En and En star are bounded away from 0 or infinity. This is what we call the semi-normalization of the basis. So if you have the three properties, then your collection is a basis. Now, this basis is not necessarily Schauder or Markushevich, because for a Schauder basis, you need to put them in some order. Right? But here we do not require any order at all. In fact, if you permute your basis, then you still have a basis. So that is the definition of a basis. And then we will talk about how we might approximate a vector. So if you give me a vector X in the space, then the question is how might we approximate X with some linear combination of vectors in the basis? And the most convenient way is to look at the linear combination of the first m vectors. So that's why I have the summation of En for n runs from 1 to m. So this way you are using some ordering because you're looking at the first m vectors in the basis. There are two drawbacks to this method. The first drawback is that this has a low level of accuracy because you will see why later. Later we introduce some methods that might increase the level of accuracy. And second, this is order dependent, right? Because you are talking about the first n vectors of the basis, but in our definition of a basis, we do not care about order. So this somehow contradicts our setup of a basis. So we need another method to approximate a vector, and this was introduced by Kojagun and Chazakov in 1999. What they had was the thresholding greedy algorithm or the TGA that we will now describe. But before going to the TGA, we will need to talk about greedy sums and greedy sets. Okay. You let n less than infinity be the set of all finite subsets of the natural numbers. And for every x, you can associate x with a sequence of scalars, en star x. And this sequence of scalars will be either the real or the complex numbers.
Mhm.
If you give me a finite set A, then PAX is the projection of x onto A, which is the summation of en star x, en for n in A. So now we can define a greedy set. A greedy set of x of order m is a finite set of size m such that the coefficient of x in lambda is at least the maximum of the coefficient that is not in lambda. So, so this is how you define a greedy set right here. Okay. You want anything inside the set to be at least the maximum of the things that are outside the set. And the corresponding greedy sum is simply the projection of x onto lambda. And finally, GXM is the set of all greedy sets of x of order m. Now, this definition already tells us that greedy sets are not unique, right? Because you can have a vector that have two equal coefficients. And if they have two equal coefficients, then the set of greedy sets, I mean, the greedy, a greedy set there might be many greedy sets. Okay, so that is how we define greedy sets and greedy sums. Now we go on to the TGA. And again, it was introduced in 1999 by Kojagun and Teleko. The TGA is a map that maps X to a sequence of greedy sums. So each of these is a greedy sum. And the size of the greedy sum increases from n equals 1 to infinity. So you see that for every x, we have a sequence of vectors. And the sequence of vectors actually is a sequence of greedy sums. And again, this method is order free because if you have a largest coefficient in some order, then you also have the same largest coefficient in other orders of the basis. Okay, so question is, does the TGA converge to X or not, right? Now we choose some projections to form a sequence, and we wonder whether it converges or not. The answer is not necessary.
Yeah.
And there exists for basis that the convergence happens, we say the basis is quasi-greedy. So this must hold for every x and for every sequence of greedy sums. If you have this property, then the basis is quasi-greedy. And when you look at this convergence condition, you might wonder, does this convergence imply boundedness? Because like in the Schauder basis, right, the convergence actually imply boundedness of the partial sum operator. So in this case, we also have the same equivalence here that your projection onto greedy sum is bounded by x. Okay, but you have to assume that the basis is Schorn. So what is a Schorn? What is a Schorn basis? A basis is Schorn if the closure of the span En for every n in A, for any set A, is equal to the set of all vectors whose port is in A.
Mhm.
So if you have this condition satisfied, then the convergence here is equivalent to this boundedness property. What this property says is that for every x, if you give me a greedy set lambda and I project onto the set lambda, the new vector is always bounded by the original vector up to a constant c, a universal constant c. Yes, another property that we care about is unconditionality. This property says that for every x and for every set A, the
Sorry.
projection on, yes.
Sure. Is there a filter-based structure on your greedy set? Is it true that intersection is again from GXM?
No. If you have two greedy sets and you try to intersect them, you do not have a greedy set.
Okay, so no any structure there, right?
I would say no. There's no intersection property for them.
Okay, sure.
They have a union property. I believe union is good, but intersection is not good.
Okay, thanks.
So this property says that you project onto any set A, and the new vector, the projection is bounded by the original vector. Now, you already see that this property is stronger than quasi-greedy, right? Because for quasi-greedy, you only have the boundedness when you project onto greedy sets. But now you can project onto anything, and it's still bounded. So that's why we say unconditional implies quasi-greedy. Here are some examples of unconditional or not unconditional basis. So if you look at the hard system, if P is greater than 1, then the system is unconditional. But if P is equal to 1, then the system is not quasi-greedy, not even to mention unconditional. Here's another one. The fixed system is unconditional if and only if we have P equals 2. If P is not 2, then it is not quasi-greedy. So again, this is maybe the key takeaway from this section of the talk, that is unconditional implies quasi-greedy. But there are bases that is quasi-greedy but is not unconditional. So here's one. If you look at the completion of C00 with respect to this norm, then the canonical basis is quasi-greedy, but it's not unconditional. This example is also due to Koyagan and Chalako in 1999. So that's the end of section 1. Now we move to discuss different greedy type bases, almost greedy, and how we characterize them in some classical results. Okay, so this is a definition by Koyagan and Chalako in 1999. They define a basis to be greedy if it satisfies this inequality. This inequality says that if you look at the error coming from the TGA, right? This is the distance between x and the greedy sum. Right? It is always bounded by the distance between x and any linear combination of vector in the basis. Then the basis is said to be greedy. So on this side, you see that this set A, it has size bounded by M, right? And this M is the same as the M for the size of lambda. Okay. This inequality says essentially that the thresholding greedy algorithm gives us the best approximation that we can possibly have, right? up to a constant C. So now this property at the first glance, it is not easy to check, right? Because of the infinitum here, it is not very easy to check. So the question is, can we characterize bases that have this property? And the answer is yes. But before that, we need to define a democratic basis. A basis is said to be democratic if you give me two sets A and B, and if the psi of A is bounded by the psi of B, then 1A is at most 1B up to a constant C. It doesn't matter where the position of the set A and B are. And here,
Indeed, democratic.
I'm sorry.
Oh, yes, please continue.
Yeah. So here, this is the result by Croydon and Chalakov. They show that the basis is greedy if and only if it is unconditional and democratic. So I want to emphasize that you see the two properties on the right here, they are relatively easy to check, right? Compared to being greedy. So that's why this is a very nice and very classical characterization.
So what has been 1A, 1B?
Oh, I'm sorry. 1A is, I should mention it here. 1A is the indicator function at A, meaning that you sum up all the vectors in the basis that are in A. Good question. I'm sorry about forgetting to mention the indicator function. So if the norm of this vector 1A is bounded by the norm of 1B, then you have democratic. Okay. And then we move forward to 2003. This is the result by 4 authors, Diogoth, Carlton, Katarova, and Kyolakov. They define a basis to be almost greedy, right? If it satisfies this inequality. This inequality, instead of looking at all the linear combinations, right? You now only look at the projection onto the set A. Okay. So of course, if you look at only at the projection, then this condition is weaker than the condition for being greedy. Right? That's why we call it almost greedy basis. Now, if you have this condition, so the question is the same: can we characterize almost greedy basis? The answer is yes. They provide an almost the same characterization, but they replace unconditional by quasi-greedy. Remember, I mentioned before that quasi-greedy is weaker than unconditional, right? So if they replace unconditional by quasi-greedy, so this is a characterization of being almost greedy. I want to squeeze in a result that we recently obtained. This is my joint work with Beres Satagi and Berna. What we showed was this. We show that in the definition of being almost greedy, you choose any set A randomly, right? But here, in fact, it is sufficient to just project onto intervals. So instead of all the set A, you can project on intervals. And even though this condition may look weaker than this condition, they are in fact equivalent. Another way to look at this, maybe another surprising way to look at this inequality is that this condition depends on the order of the basis, right? Because you look at intervals, and when you talk about intervals, you're talking about order. But this condition is order free. It doesn't care about how you order the basis. So it is kind of surprising that we can find an equivalence of we can find a characterization of being almost greedy by something depending on the order of the basis. The next slide will be about variety of greedy bases. So how common are these bases? If you look at this theorem, then they are not very common, right? This theorem says that these spaces do not have any greedy bases. because for any unconditional basis, it is always not democratic, so it cannot be greedy. But we know that there exists, but we have some result about existence of almost greedy basis. So this is a result by DKK, Dearworth, Carlton, Kozarova in 2003. They show that if X contains a complemented copy of LP, then X has infinitely many inequivalent almost greedy bases. So even though a space may not have a greedy basis, they may have a lot of almost greedy bases. That's why we say almost greedy bases are much more common than greedy bases. However, I want to end this section with a remark that we will see more in the next section. Right? But this is the remark that I want to make. Almost greedy bases are not far away from being greedy. So you will see why in the next section. So now we talk about how we might relax the optimality for the thresholding greedy algorithm. So this is a result by DKKT in 2003. They show that this condition, this inequality, is equivalent to being almost greedy. Remember, almost greedy is only projections, right? Involves only projections. But they show that if you restrict the size of set A down to m over lambda instead of m, if it's m, then this condition is greedy. But now they do m over lambda for any lambda greater than 1. By doing so, this condition is now equivalent to almost greedy. So this is a very nice result because it says that almost greedy is so close to being greedy in terms of the size of approximation. Even though almost greedy might not give you the best m-term approximation, it gives you the best m over lambda term approximation. So the question we have is, what if we resize the approximant on the right side in the condition for almost greedy basis? Because if you look at here, they just reduce the size of A in the definition of being greedy, right? So what happens if now we do it for almost greedy basis? Do we have something new or not? And here's what I recently obtained. We do not have anything new. So if you have the projection on this side, then and you restrict the size of A to m over lambda, then you still have almost greedy basis. Right? So nothing new. This you may think of this as a disappointment, but it turns out that we may need this result later in one of the proof that I will present to you later. So let me summarize a bit. This is the definition of almost greedy. Right? Almost greedy, you have greedy sums on the left, on the right, you have projective approximants. Right? And if the greedy sums have size m and the projective approximants have size m over lambda, then we recover the definition of being almost greedy. That's what we see in the result I presented earlier. There's nothing new. No new greedy property. So the question is, what if we reduce the size of the approximants further down to log m or square root of m? This will even worse than m over lambda. Then do we have some new greedy property? So to do so, I introduce a collection of function f. This function f, you can think of them as being, concave, continuous, and you see the idea here is that after you go over 1, 1, right? After you go over the point 1, 1, all these functions lie below the 45-degree line. Before 1, you can go above, but after 1, you need to go below the 45-degree line. So I introduced this collection F, and I also put a lot more conditions on it, like being differentiable or being continuous. But I do so just to avoid some technical details, but we can relax them. But the argument will not be concise. I believe it will involve a little bit of technicality. So these functions include root x, log x, or square root of log x. So a bunch of functions for you to choose from. And using this collection F, we can define F greedy or F almost greedy. Right? What I did was I only replaced A, the side of A bounded by Fm. So instead of M, you have Fm. Right. So this is the concept of F greedy and F almost greedy. The classical definition involves M here and M here, but now we do it for Fm. So this is definitely weaker than the definition of with A less than M. That's why we say we are relaxing optimality of the algorithm. So you might wonder, like, okay, is there any use in introducing this new notion? What is the purpose or what is the motivation for this? And I answer it in the next slide here. We have a bunch of motivation examples. The first example comes from this space, LP, LQ. This space does not have any greedy basis, but it has an x to the p over q greedy basis, and x to the p over q is in our family F, right? The multivariate class system HPD here, p has to be different from 2 and d has to be at least 2 or greater than 1. Then this system HPD is not almost greedy, but in our language, it is x to the 1 minus epsilon greedy for any epsilon greater than 0. So it means that even though this system is not almost greedy, it is very close to being greedy, right? Because you can choose any epsilon in the power here. The last motivating example is this space, and this space is coming from a recent result by Bernard, Dearwood, Katarova, Olberg, and Wallis, right? They construct a basis that satisfies some certain properties, like being partially greedy. I didn't mention partially greedy in this talk, but you know that they construct a basis that is partially greedy but not almost greedy. So even though this basis, if you equip, if you take the completion of C00 with respect to this norm, then the canonical basis is not almost greedy, but it turned out that it is square root of x greedy. So you see that how we can put our new definitions into context, that our new definitions of F greedy or F almost greedy give us some new perspectives on different greedy type properties for bases. Okay, so the next section is, now we have introduced the definition and some motivation example of F greedy type bases. Can we characterize them in the same sense as what we have in some classical results? So to do so, we need to introduce a bunch of definitions. And in this definition, it is the modification of F of democratic. Right? Here you have F disjoint democratic. You need to take two sets A and B disjoint, and the psi of A is bounded by the psi of FB. Then the norm of 1A is bounded by 1B. If you have this property, right here, then you say your basis is F disjoint democratic. F unconditional. So this is a restricted version of unconditionality, right? Here you still project on the set A, but the set A now cannot be anything. It has to contain a greedy set of X of size at least A minus FA. So if you have this set A satisfying this property, then the projection onto onto A of X is bounded by X for F unconditional basis. Now, if F is the identity function, then you see that this difference is 0. So you do not put any extra condition on the set A. And that's why we say F unconditional is equal to unconditional when F is the identity. Right? So using these modifications, we have the following results. So let me describe each of the results. The first two results here give us characterizations of F greedy and F almost greedy basis. Right? So F greedy is equivalent to F unconditional plus F disjoint democratic. F almost greedy is equivalent to quasi greedy plus F disjoint democratic. The third result is surprising. This result says that if you give me any function F that is different from the identity function, then you have the equivalence between F greedy and F almost greedy. So what it says is that it doesn't matter if you take the projection of the linear combination, right? F greedy is always the same as F almost greedy, assuming that F is not identity. The fourth result is that if G is bounded by F, then F almost greedy implies G almost greedy. If G over F approaches 0, then there exists one unconditional basis that is G greedy, but it's not F almost greedy. I highlight the two results here in red so that we can go into the detail in a bit of the proof sketch, not the whole proof, but only sketch. So let's try to prove this theorem. This theorem says that if G is small of F, or if G over F is going to 0, then there exists an unconditional basis that is G greedy, but it's not F almost greedy. I will only focus on the F almost greedy part, like not F almost greedy. And here is a construction. You construct a collection A, and A is a set of all finite sets such that it is non-empty and it satisfies this property. It satisfies this inequality. Okay. And then you take the completion of C00 with respect to this norm. Okay. Then clearly the canonical basis of xg is a completion is one unconditional, right? Because you take the absolute value of these numbers. But let's do some calculation. If you look at this vector, it is a bunch of ones at the beginning, like n1. Then the norm of this is at most gn over g1. If you look at this vector, but now you push all the ones to the right sufficiently far enough, right? Then the norm is fn. But if you look at the ratio of 1bn over 1an, it is approaching infinity. Okay? Because g over f is coming to infinity, is coming to 0. So that's why f over g is coming to infinity. Now you see that you have a bunch of sets, two sets, and they satisfy the condition in the definition of f democratic, but the ratio is unbounded, right? So it doesn't satisfy this condition. The two sets an and bn doesn't satisfy this inequality, right? Because it's not bounded by C. So the basis is not F disjoint democratic, or and so by the way we characterize the basis, it is not F almost real. So this is just a remark that we can show that the basis is G disjoint democracy, but and you combine it with unconditionality and it gives you G with it. But the basis is not F with it, or not F almost with it. Okay, I want to end this section with a particular example, and this example is again from the hard system PhD. Here I assume that D is greater than 1, or D is at least 2. I should say this is the multivariate hard system, not the hard system. And P is greater than 2. If you fix epsilon greater than 0, we want to show that the system is x1 minus epsilon really. Okay? And how do we show that? We know the system is unconditional. So we want to show that the system is x to the 1 minus epsilon disjoint democratic. So how do we show HDP is x 1 minus epsilon disjoint democratic? Well, we will use this proposition. This is the result by Hiron, Pilkat, and Chalokov. They prove that if you look at the indicator function, right? This is the indicator function at A, 1A. Then by choosing H and cleverly, the lower bound can be obtained at m to the 1 minus m to the 1 over p, and the upper bound will be almost the same, but it is multiplied by a log function. This log function shows that because the upper bound and the lower bound are not of the same order, right? Then this system is not democratic, because in order to be democratic, the maximum and the minimum must be of the same order. But here you have different order, right? At least by a factor of log n. So that's why the system here is not almost ready, because it's not democratic. But it turned out that it is x to the 1 minus epsilon disjoint democratic. We introduce the epsilon here to take care of the log function. Okay. And now we can see the proof. Let's choose any set A and B, okay, finite sets, such that A is bounded by B to the 1 minus epsilon. And then we can choose n to be large enough, such that if x go over n, then this function as a power of x will dominate the log function. Okay. This is doable because, right, you have power function dominates the log function. So here is a proof. This look a bit overwhelming, but it's not. We can assume that A is at least n, right? Because we only care about the case when the size of A and B are sufficiently large. So we assume that A is at least n. And then we define this function PD to be equal to the power of the log, just to be concise. Right? It is no math, it is just notation. Then you have what? You have 1A is bounded by this. This first inequality here is due to this theorem. You see that I just replace m by the psi of A. Okay. So this is due to this. The next step, I just replace A by B, because the psi of B is greater than the psi of A. So I can replace A by B. The next step is coming from here to here. I'm using this inequality by how we choose n. Right? Now we have the equality, and finally, this inequality is due to the lower bound in the proposition. So you see that we go from 1A to 1B, right? Go from 1A to 1B, and this is true for any set A and B with the sign of A is bounded by B to the 1 minus epsilon. So that's why we say, okay, the system is X to the 1 minus epsilon disjoint democratic. So that's the end of this section. I want to devote the last section to try to explain to you this equivalence, like why the definition of F with D and F almost with D are equivalent in the case of F is non-identity. Remember, for F with D, we have the linear combination, right? But for F almost with D, we only have projections. So this is an unexpected equivalence if we think about definition. But how can you explain this? Okay. So why is equivalence believable? Why don't we look at the extreme cases of function in F, right? Because if this equivalence hold for the extreme cases, then we expect them to also hold for anything in between, right? And well, the two extreme cases are functions that grow linearly. Remember, when I have a graph of this kind of function, the best we can do is that they grow linearly. So that is one end of the picture. The other end consists of bounded functions. These functions do not grow at all. They, after a while, they are bounded by, I mean, they grow so slowly that they are bounded by a constant. So let's see what happened in these cases. Well, for bounded functions F, it is easy to see that they are equivalent. In fact, F with D is equivalent to F almost with D, and is equivalent to quasi with D. Okay. That is for bounded functions. For linearly growing function, then we have the following. I would like to recall a result by DKKT, right? They prove that X over lambda with D is the same as almost with D. This is the result I showed you way at the beginning of the talk. They are equivalent. And by a result that I call that I also mentioned earlier, then X over lambda almost with D is equivalent to almost with D as well. Right? Remember, when we reduce the size of almost with D, we do not have anything new. This is where we now use this result here. So of course, if you see these equivalences, then X over lambda with D is the same as X over lambda almost with D. So now you see that for the two extreme cases, we expect the equivalence for all non-identity F in the family. Okay, so this is just give us some intuition behind the scenes, but now we can come to the maybe a more rigorous proof. I want to mention two very nice results that I have encountered and also used a lot in the topic. The first one is due to Gutasik in 2000. What he proved was if you have a quasi-greedy basis, the indicator function, the norm of the indicator function is quite stable. What I mean by that is it doesn't matter how you multiply HEN by some epsilon n, as long as epsilon n have modulus 1, then the norm, it doesn't change much. The norm stay very stable up to some constant C1 and C2. Okay, this is the result by Gutasik. Then another result also due to Gutasik, and I would say also due to DKK in 2003. I'm sorry, I think I should mention that this inequality here is called the UCC or the unconditional for constant coefficients. Now we come to another name, another property, which is the TQG, or truncation quasi-greedy property. This property says that if you have a quasi-greedy basis, then you give me any vector x and any greedy set A of x. If you multiply the minimum of the coefficient in A by the norm of the indicator function at A, with keeping the sign of x at these vectors, then the resulting quantity is bounded by x. We will use these two properties in our proof of the equivalence. Okay, so we need to show this, right? And we need to show this for the case when fx over x is coming to 0, because if fx over x is bounded below, then fx grows linearly, and we already see that in the linear case we have the equivalence. So that's why now we only focus on the case when fx over x is coming to 0, and we only need to show one direction, right? Because the other direction is obvious by definition. Okay, assume that we know this result. This is a result that we proved earlier, but we're gonna use them in the proof of the equivalence. Okay, assume that we know these characterizations of F greedy and F almost greedy basis. Then, in order to prove this implication right here, given that we know this, it suffices to just prove this implication, right? Quasi-greedy plus F disjoint democratic implies F unconditional. And again, for your reference, I mentioned here the definition of F unconditional. Again, if you project X onto a set A, such that A contains a greedy set of X of size at least A minus F A, then the projection is bounded by X. Okay. So how do we prove this implication? Well, assume that our basis is quasi-greedy and F is democratic. We fix any X, right? And we choose the set A that can be written as a disjoint union of E and F, where E is the greedy set of X of size at least this, right? This is a goal. We want to prove that PAX is bounded by X. Now, what we have right away is that PEX is bounded by X, because our basis is quasi-greedy, right? And E is the greedy set of X. So of course, by the quasi-greedy property, you know that PEX is bounded by X. So in order to prove that PAX is bounded by X, we only need to prove that PFX is bounded by X. But now remember, F can be anything. F doesn't have any restriction at all, right? The only restriction is that the sign of F is at most FA. That is the only restriction. So we want this. To do so, we just let alpha be the minimum coefficient in the greedy set, and beta be the maximum element or the maximum coefficient in F. Then clearly beta is less than alpha, right? Because E is a greedy set and F is outside the greedy set, so beta is bounded by alpha. Okay, so let me explain this calculation here. Because we assume that fx over x is coming to 0, then we can assume that the psi of E is about the psi of A, right? Because you know that the psi of E here is bounded by is at least A minus FA. But now if FA over A is going to 0, then you know that E is approximately A. Also, because E plus F is A, and E is at least A minus FA, then F is at most FA. But A is about the same as E. So FA is, you can think of it as FE as well. The reason why we need this inequality here is that now you have two disjoint sets, E and F is at most FE. So you can apply F disjoint democratic to the two sets E and F. Okay, so the first inequality here is due to convexity, right? Because you pick beta to be the maximum coefficient in F. So this is convexity. The next one is UCC. Remember, if you have a quasi-greedy basis, right, and UCC means that if you change the size of if you change the scalars, the norm doesn't change much, right? As long as the scalar has modulus 1. When you go from here to here, I only replace beta by alpha because alpha is at least beta. And also I use F disjoint democratic to move from the set F to the set E. See that? From F to E, right? I use F disjoint democratic because they are disjoint and they satisfy this inequality. Now the next one is UCC. I simply multiply HEN by the sine of EN star X. Okay, so this is UCC. And the last one is TQG, right? TQG because E is a greedy set of X. So I have this inequality. So now you see that we already bounded PFX by X. And that completes our proof because we have the boundedness for PEA and PFX. So we can bound PAX by X. Here are some references that I have. And yeah, so I hope that we have a good discussion of the TGA and different greedy type bases. And also we discussed I could say quite in depth the problem of relaxing optimality and some recent results of characterizations and also about the equivalence between F greedy and F almost greedy bases. That's all I have, and thank you.
Thanks a lot. So, no, well, let us at first applaud our speaker and then questions, please, gentlemen and ladies. Yeah. Maybe.
Do you have any result of construction type? For example, getting the projective tensor product of two Banach space and getting two greedy bases and what can happen in the tensor product or even in the Banach space direct sum. Do you have this sort of results or?
Not that I have, but I know this type of result. That is a very good question. Let me go back here. I think what you are talking about might be related to this. So the hard system here, the HPD. So this is basically a tensor product of a bunch of the hard system in one dimension. But if you have one dimension, let's say d equals 1, let's say d equals 1, then your basis is greedy, meaning that it is unconditional and democratic. But if you have d is greater than 1, then the story changes by a lot. It is no longer greedy, it is actually not almost greedy. So doing the tensor product might bring us to some unexpected result. Okay.
I see. But for direct sum, no problem, right? You can by somehow change the norm.
You say that the
for standard direct sum, for example, L1 sum.
Direct sum change. Direct sum also change. So if you look at the LP and LQ here,
Yes.
LP of course is greedy, But when you
Oh, yes,
direct
yes,
sum with LQ,
that's right.
it is not democratic. So it is very easy to lose democracy.
I see.
Yeah.
Okay, okay, maybe the supervisor will give us some overview. Or, yeah, Timur, okay. He is silent. Yes, no, so I can only my own expression. Very, very well presented talk about that.
Thank you.
Certainly it is very interesting and the results are impressive, but very clear, presentation. So
Yeah,
thank you
for
very
inviting
much again. Maybe other questions, not? No.
I have a little question.
Yeah, please.
At the very beginning of your talk, you mentioned some relation between greedy and shoulder bases. So could
Yeah.
you show the slide once again, please?
Somehow I cannot click here, so I need to go slide by slide. I guess you are talking about this slide, maybe?
Maybe a bit later.
Okay.
So you said something about relation to shoulder bases.
The only time I
It was
mentioned,
quite another thing, he said. And you want details, yes?
Yeah, I think this
No,
was
when you said about strong bases.
oh, I see. Here, yeah.
No, shoulder bases are strong. Okay, I see. And so
Yeah.
my question was about the converse. Are there any examples of
So-
strong bases which are not shoulder bases?
So if you, that's a good question. So shoulder bases are strong, and let's say you look at an unconditional shoulder basis, like let's say the summing basis of C0, right? It is shoulder, but it is not conditional. It is not unconditional. Then there must be some permutation of the basis that make it no longer shoulder, right?
Mhm.
Because it's conditional. So you can permute it to make it no longer shoulder.
Mhm.
But it is still strong because you see this property of being strong. It doesn't
I
depend
see.
on the ordering.
Mhm.
Yeah, that's a very thoughtful question. Thank you.
Okay, thank you.
Okay. So other questions there are? No, I see. No, so again, let us thank the speaker for a very good talk.
Thank you very much.
Yes, and next, our next speaker is just the person who had most of questions today, very natural. Professor Dossi next time, and then we shall see what will be next. So thank you very much for all present, for speaker, for his supervisor, and for other people, and meet again the next week. Bye-bye.
Well, I should only say that this work is entirely due to the current speakers. My input there was really, if not zero, then epsilon. So all the laurels go to the speaker.
Yeah, but
About
it's not-
epsilon, we know only that it is positive.
Yes, it's positive.
Nobody
It's
said
positive, yeah.
that epsilon is
I certainly hope so.
okay. Okay. Thank you very much. Okay. So,
Okay.
ladies and gentlemen, we part, but I hope only for a week. Bye-bye.